So welcome to the revision video for iGCSE Physics. This is just one whole topic. There are some more videos which are individual subsections, but this is for if you finish the entire topic. So there are 8 videos in the series. If you like and enjoy, please subscribe. Okay, so this is another iGCSE introductory topic video. So it's 1B motion that we're looking at, key physics. So what have we got then? So we've got quantities and symbols. So we're looking at, you need to know D is a measure of distance in meters, time is time in seconds. So pretty straightforward, T for time, D for distance. But then it gets tricky. So we've got something called a vector, and a vector is not just a quantity, so distance and time are just quantities, but vectors have a direction as well. So we say that they have magnitude and direction, whereas the scalar just has magnitude. So displacement, a measure of how far you've moved from an original point. So that could be a mass on a spring moving up and down, or it could be a runner on a running track that comes back to 0 point again. We've got V for final velocity in meters per second, or ms minus 1. U, initial velocity. A, acceleration. That's meters per second squared, because we're dividing the speed by time again. And you might see delta V being a change in velocity. Often that's not used, but it prepares you for A-level. Maths then, so we usually calculate its average speed for an object because the speed changes during the journey, so it's rarely constant. So average speed will be your total distance divided by the time for the journey. To work out the acceleration of an object, it will be acceleration is change in velocity over time taken. Change in velocity is very important. So it's either V, take U, final take initial. That takes account if you don't start from 0 at a graph, you might be starting at 10 and go to 30. So it'd be 30 take 10. And you could write delta V if you know it's a change. The equation for motion when you don't know time. Now you don't have to derive this, but you have to know that the final speed, V squared, equals initial speed, U squared, plus 2 times the acceleration times the distance moved or displacement. Now they use the S there. You've got to remember that that is displacement. 3 key graphs to look at. So distance time graphs. So you've got to basically recognize what happens with these types of graphs and match it to scenarios. And in this case, I can work out if I do the distance, anywhere on the graph divided by the time, anywhere on the graph again, anywhere, it will give me the speed, and I'm traveling at a steady 30 meters per second. We've also got a velocity time graph. Now, if you have a velocity time graph, the area under the graph, so it could be a rectangle, could be a triangle, could be triangles and rectangles, is just the distance traveled. It's expected you could work out the area. So in this case, it's 50 times 5 divided by 2, and that gives you the distance traveled. And the third graph that we need to know is a speed time graph where we work out the gradient. So it looks very similar to distance time, but notice this is speed. If I do my change in speed divided by the time taken for the change, I get my acceleration. And that's the steepness of the slope or the graph. And we also should know that negative gradients indicate the object is decelerating. So that's the key stuff for motion, 1B. Okay, so this is a quick topic introduction for 1C, forces and motion, iGCSE physics, with forces, motion, or movement and shape. So we've got a few tables of information. So we need to know the term scalar, vector quantities, so the difference, one has magnitude or size and direction. Distance D instead of S for displacement. So we've got distance moved and direction in a plus or minus, or just how far you've moved. The resultant force is when you add all forces together on an object, and it usually creates an acceleration. We've got Hooke's law, which is extension of a spring is proportional to the force applied. Contact forces, so where objects touch. Non-contact forces, objects don't touch. So could be forces created from gravitational fields, magnetic fields, electrostatics. Elastic behavior, so when a spring is deformed and then it returns to its original size. Free body diagrams, so labeled diagrams with the forces clearly labeled, kind of like this bit, but a little bit more complex. We've got to do all that stuff there. We should know our different types of force, so friction, electrostatics, tension. So that's when we're pulling something out. Up thrust, so forces pushing on an object, a liquid or a gas. So we don't use that for solids. Magnetic forces between two magnetic poles, gravitational forces between two objects with a mass, or air resistance, or you could also call that drag, caused by air pushing on an object. So my pictures here clearly show different scenarios about stretching, compression, pushing, torsion, and turning. We need to know about Hooke's law experiment, or this proportionality idea. You should be able to describe how that works, that kind of thing. We've also got some formulas. So coming from the previous unit, you still need to use total distance traveled over time taken is average speed. Average velocity would be the final displacement over the time taken. We should know about the force, is the spring constant K times extension X. It's a bit of a stretch for iGCSE, but sometimes they could ask you to work out the gradient of the graph, which might be quite cool. Definitely normal GCSE, but they often just want the simple bit for basic spec at the moment of this. A resultant force would just be a big force, take a small force. So if we've got two forces acting on an object, we can do one take the other. That gives you size and direction. So there you go. That's forces and motion. 1C, quick summary. Okay, so this is another little summary for this time section 1C, part 2A I've put it as, which is for the iGCSE Physics, movement. So we're looking at weight is mg and F equals ma. So key parts are, we've got the acceleration formula, F equals ma. I prefer to write it as the ratio of force and mass. So for newtons per kilogram equals a measure of your acceleration. So how fast are you changing your motion? There's also the relationship between weight mass and gravitational field strength, which is basically the same, isn't it? But it's operating downwards towards Earth, which is when we use this terminal velocity idea. But we've got weight is mg, g on Earth is 10 newtons per kilogram, 10 meters per second squared on Earth. There are different values for different planets as well. So that's something to think about for exam questions. But you just have to know the one for Earth and then use that and then make changes from it. 3 laws for Newton. So we've already talked about F equals ma, which is the second law, this one. So the orangutan only going to get up when there's a resultant force or change in momentum. The top one, inertia. So things carry on doing what they're already doing. So if you're already sat there, you just keep on sitting there unless a force acts on you. If you are going to, if you're already moving, you just keep going until a force acts upon you. So you could be traveling at a steady speed, which is slightly confusing. So Newton's first law, Newton's second law. Third law, if you sat on the floor, there's an equal and opposite reaction force of the same type acting up on the orangutan as the weight of the orangutan acting down on the floor. So you've got to have two objects, they've got to be the same type of force. Terminal velocity, when you fall or drive at constant speed due to balance forces, so you get out of the plane, you've got weight, you've got maximum acceleration, and as you go faster, the drag force acts up and gets bigger and bigger and bigger, but the weight eventually, they two balance out. Weight doesn't change, but drag gets more. When the drag is at its maximum value there, we will fall at a steady speed because there's no external forces acting, so the acceleration is nothing because F over m is naught. There's no acceleration. So you've got to look at terminal velocity. Stopping distance then is a combination of this sort of diagram, factors, and the graph itself for stopping distances. So think about if you are seeing a hazard and you visualize it, you think about it, you think about it, you think about it, you're still moving for a period of time, which is this top section here, this rectangle. And then I actually put my foot on the brake and I start to brake and I slow down and I stop. So the whole of the two distances added together is the stopping distance, which is also the area under a velocity time graph. So triangle plus rectangle gives me what I need. Stopping distance factors, then we need to think about if you were distracted by the passengers, you were drunk, you'd taken drugs, so you're intoxicated, that would be the same marking point. People are talking in the car, distracting the driver as well. That could be another one. So it could be any other name, form of distraction. I suppose these two are the same point. But it's noise, it's distraction. Could be something outside of the car as a distraction as well. Braking, so worn tyres, low tread pattern or grip. Ice, gravel, oil on the road. Talking about how it lowers friction is key. Worn brakes, poorly maintained, poor force on the disc. So it could be your brake fluid's gone a bit dodgy because it's hygroscopic and has absorbed some oxygen. Also, if the mass of the car is bigger and the passengers, so maybe more passengers, which could also cause more distraction, you've actually got more kinetic energy. So you've got more energy store to lose because the velocity has to be converted into thermal as we lose our kinetic energy. So you've got stopping factors, distance graphs, and distance sort of diagrams to be able to explain. And we've got all of the Newton's law stuff. That is the topic. There you go. So that's topic 1C, part 2A. So this is 1C section 2C for moment. So it's an iGCSE quick summary page. So what have we got in this unit? Well, there is key formula. So moment is force times perpendicular distance from the pivot. So just like this picture here, perpendicular means basically 90 degrees. So there's my pivot point, 12 centimeters, would be 0.12 meters. 10 newtons is how much I pull down with. So 10 times 0.12 gives me 1.2 Newton meters. That is your turning effect. If I move the hand away from the pivot point, I will get a bigger turning force. I could also apply a bigger turning force there, and that would provide a bigger moment. You need to know the principle, which is the best thing to write down for any exam question. Clockwise moments will equal the anti-clockwise moments, and they could either have, you can see, that's clockwise, that's counterclockwise. Objects will stay where it is if they cancel out, or if not, make an object turn. It will also make irregular objects move as well until they find the center of mass. So you should be able to describe an experiment where you put holes in a piece of card, or you could hang an object to different places. You let it dangle, you draw a line, you move to another hole, it dangles a different place, and that gives you the center of mass. And we need to know the center of mass is basically and when we say one important principle in physics is that any object, however sophisticated, large or complex, can be treated as a point mass. So it's where we can work out the effect of the forces and show that all the forces act through this single point. So on that irregular object, it's there. For a solid block, it would be the diagonals, a cylinder in the middle. Center of mass here could be a beam on a pivot point. Okay, so you should know about different objects, but they'll give you some formulas if you need to do anything fancy. Toppling or equilibrium, so the weight acts from the center of mass, and so if it's within the base, it will be stable, and it will then tip back to its original position. But if the line of action of the force acts outside of the base, it will topple over, so velocity will topple. And then we also need to have another look at Newton's third law. So the two forces act on two different bodies, i.e. A and B. Forces are always of the same type, i.e. both gravitational, both electrostatic, magnetic. Forces are equal in magnitude and size, and they're opposite in direction or collinear. So there you go. That's the moments topic. So this is another quick iGCSE summary video for an intro. So we're looking at key mass in this unit for momentum as being the mass times the velocity. Momentum has the symbol P. That's what we usually use, lowercase. And of course, you've got M and V for mass velocity. Force would be the change in momentum over the time taken. Well, that's mv. So v would be your final velocity, take initial velocity divided by time. Sometimes that formula simplifies. So if I've got mv, the final velocity is 0, we just have f is minus mu over t, which makes it quite a lot easier. Calculations, you need to be able to do P is mv, so mass of an object times its velocity gives you momentum in kilograms meters per second. We need to be able to think about impact forces. So F equals ma, which is from a previous unit. A is v take u over t. I need to substitute the a out of the first equation. You can see the a is the same to give me F is m v take u over t, which is the original form we've got at the top. So you need to be able to understand how impact forces work. And of course, your impact force would be from your change of momentum over the time taken. So of course, if I have an airbag or a crumple zone in a car, the rate of change in momentum then is smaller. So it's all about increasing time because the mass of the car you can't get rid of. So you have to somehow make the time longer, and that makes an FT graph have a smaller maximum force, a smaller peak. Newton's 3 laws of motion, which we've already dealt with, come into it as well. So velocity of a body remains constant unless the body is acted on by an external force. So resultant force is naught is law 1. Law 2, second law, so the acceleration of a body is parallel, directly proportional to the resultant force F, and inversely proportional to mass m. So F equals ma, or F over m is a, of course. Third law, the mutual force of action and reaction between two bodies, i.e. body A, body B, object A, object B, is opposite collinear. Collinear means in a line, so force A equals minus force B. We've also got elastic collisions to look at as well. So imagine we have two trucks, and so the red truck has momentum, hits the blue truck. The trucks link carry on at a lower speed. We have to think about the idea that momentum is conserved at the start and the end. So I set up a formula where the mass of the red truck times the velocity of the red truck at the start plus the mass of the blue truck and the velocity of the blue truck at the start, which could be 0, but we're going to put it in our formula anyway, would equal the mass of both of them, because remember they're linked, times the new velocity. Now, if you know certain things, you can work out something that's left over. We also need to do explosions, which is bullet explodes or is fired from a gun. The bullet and the gun have different masses. They share the momentum and velocity of the explosion. Momentum at the start and the end is naught and conserved. So naught would equal mass bullet times velocity of the bullet plus mass of the gun times velocity of the gun. I move one to the other side, and then one becomes a negative of the other, which takes care of the velocities, because obviously they are going to be opposite, not equal, because the masses are unequal. So the object with the biggest mass goes slowly, the object with the smallest mass goes quick. So there you go, projectile motion. So that is momentum.